Okay, just to recap. So basically, for question 3, part 3, just an illustration. Yeah. You have a function with a sine function, and your set E is running from 0 all the way to infinity. So FE is very simple. So along this line, right? So we make a projection of the value on the x-axis. To make a projection upwards, it touches the y-axis. It touches the function f. Then make a projection to the y-axis, right? And then you can read off the values. So if you do so, you will find that the range of values is from -1 until 1. Okay. And then when you do the inverse mapping, then your set moves from the x-axis to the y-axis. Still the same set, yeah. Okay. And since after 1, right, it hits nothing on the function, so you can basically ignore the part. Okay. After y larger than 1. Okay. And then you draw a horizontal line from the y-axis. Okay. And then when it touches the function, right, you make a projection downwards to the x-axis. Then you can read off the values. Okay. By doing so, you can actually see that the the inverse mapping of the set E, right, will give you the interval from 0 to pi, then the 2 pi to 3 pi, and so on. Yeah. So you can, if you, I hope this is clear enough. You can actually use this understanding to confirm that, confirm the result for question. For part 2, yeah, where you have actually a log function, you have an exponential function. Okay. Are there any questions? About problem 3 anymore? Okay, great. Then we can go on to question 4. Yeah. So Ida, Maisara, you can share your screen. So I've already enabled screen sharing for all participants. So I think you can directly share your screen. Okay, ready, Ida, for question 4? I have a mic question. All right. Mic problem. Okay. In that case, maybe you can go to problem 5. Dina Zaid. Is Dina here?
Yes, here, Doctor.
Okay, yeah, you can share your screen.
Doctor, I cannot share my screen.
Oh,
Because it says that you cannot start screen share while the other participant is sharing.
Oh, okay. I stop share. Okay, try now.
Okay. So for question 5, this is the sequence given, and explain why the limit of the sequence is exponent -1. So we have to show that the limit for this sequence as n approaches to infinity is equals to exponent -1. So first I let this part, this left hand side part to be y first, and then I put ln here and also here, so that we can find the limit. And then the n here I change to 1/n. So from here, if we substitute infinity in n and also n here, will give us 0/0. So we should apply the L'Hopital's rule, and then differentiate the upper side and also the bottom side, and then I get this one. And then next is I just simplify the equation, and then comes to this, the simplified one, negative n over n minus 1 give a limit as n approaches to infinity. So from here we can get -1. So just rewrite the front part here, ln y is equals to -1, and then we put exponent on the front and at the back, and then we get y equals to exponent e -1. So y here refers to the sequence, the limit of the sequence. Then we just substitute here, and we get the limit as exponent -1.
Okay. All right. Okay. Thanks, Dina. So yeah, actually, basically for this question, you can just make use of this result. You just start from this this well-known result in calculus. Yeah, the limit of 1 plus x over n power of n equals to exponential x. Then your argument is basically just this is equal to e of -1 because it just corresponds to x equals to -1. Okay, it's very short, but of course, what you have shown is kind of like. Can you go a little bit up? Okay, so we want to show limit of. Okay, you set it to be y. Then log of y equals to limit of that thing. Okay, so basically it's you yeah, actually the log function is actually outside of the limit, but because you are evaluating the argument of the log, so you can interchange the position. Okay, then you apply L'Hopital's rule. That's also okay lah. What you have done, right? Actually the purpose of this question is just to make you recall that important result, yeah, that result that you highlighted. The limit of 1 plus x over n power of n equals to exponential x. This is a very important elementary calculus result, yeah, that you will come across repeatedly many times. Okay.
Okay.
Okay. Thank you, Dina.
Okay, thank you.
So let's move on to problem 6. Problem 6 is SIT3001. Umaira. Okay.
you see my screen now?
Okay, you want to start, Cindy?
Can you see my screen? Oh my God.
Can you see my screen?
Yes.
Okay. Okay, the question given an as 2n plus 2 over 5n plus 1. So we need to show that limit n approach infinity 2n plus 3 over 5n plus 1 equal to 2 over 5 by using the epsilon definition. So the first thing we need to show that there is some n such that 2n plus 3, 5n plus 1 minus 2 over 5 is bounded by epsilon when n is greater than n. So first, we need to show the left-hand side first. This is the fnx minus with fx, the limit of the fnx. 2 over 5 is the limit of fnx. So it's equal to, we expand with the same denominator, and then we will get 13 over 25n plus 5, where this one is less than, we can see that 25n plus 5 is greater than 25n. So when the denominator is bigger than so this is less than this fraction. So 13 over 25n is less than or equal to 13 over 25n, as this is because n is greater or equal to n. So this one is less than the epsilon. So then we choose the n is more than 13 over 25 epsilon.
Okay, great. Yeah. So this completely correct. So basically up to your So you use the correct bound there. 13 over 25n plus 5. So actually I mean like you correctly bound it with 13 over 25n. Actually there are many other possible bounds lah. This is the easiest one to put, right? Even if you cannot get the idea of the bound, you can still write that 13 over 25n plus 5 is less than or equals to 13 over 25 big N plus 5, right? It will be the same, and then bounded by epsilon. Then you can solve for find the inequality for big N. It's just a little bit messy lah. So up to this point, if you understand the idea already, there are many possible solutions. Okay, because the idea is that we are studying the tail behavior of this sequence. Yeah, as long as you can guarantee that there is some threshold where the tail behavior, where the tail of the sequence, right, they will not escape from the limit by more than a certain amount bounded by epsilon, then it's already proven. Okay, because the crucial part is the tail behavior, not the behavior in the middle or some part of the sequence. Yeah, so that's why there are many possible ways to do it. So but then it's a good exercise to set simple bounds, all right, like what you have done. Okay.
Okay.
Okay. Thank you. Thank you, Siti. Then the question 7, similar kind of question. Maybe Haja can do. Siti Haja.
Yes, Doctor. Hello, everyone can see my screen?
Yeah, we can see your screen.
Okay. For these questions, let an equals to these terms, and for some epsilon more than 0, in order that this definition, what are the values that the threshold n must take. So I first solve these terms first, and I neglect, I split the terms into two, and these terms will go to 0 as n approaches infinity. And finally, I get these terms. So by the epsilon definition, we will get that these terms is less than n. So since the condition is n, small n more than or equal to capital N, so therefore we can take that n is more than the cube root of 1 over epsilon minus 1. Alternatively, I can actually neglect this 1 plus n power of 3 and just take 1 over n power of 3. And then by the condition small n more than or equal to capital N, we can also take that n more than the cube root of 1 over epsilon only. Thank you.
Okay, Steve, can you scroll back to the beginning? Yeah, okay, this part. I think we cannot, we can't actually do this operation here. Like you say that goes to 0 as n tends to infinity. That statement is true, but when you try to argue for this, you can't simplify like this. You have to take the n as a number, you can't kind of like make it go to infinity at this point yet.
I see. Okay.
So I would say some part here the argument is not watertight.
All right.
It's not completely watertight because yeah. Okay. 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 So maybe I just okay. Thanks, City. Just to make you aware that you shouldn't do the approximation at this stage. Yeah.
All right.
Okay. Maybe I just show you how I would do it.
Okay, sure. Thank you.
Okay, so we want to show that okay, so we have this thing. Okay, we want to show that there exists some n such that when your index n is exceeding this threshold, this condition will be true, right? So let's look at the left-hand side. The left-hand side is you can expand this. Okay, so this will give you n plus 1, n plus 1 plus n power 4. Okay. Now, of course, if you at this stage you start doing something like this, it's possible, but then it will be very difficult to find an expression for your big N. Okay, so we don't want that. It's too complicated, right? So we first have to find some kind of suitable bound for this expression here. All right. I would say the easiest bound is this thing, right? This is bounded by n plus 1, n plus n power of 4, right? Okay, because it's less 1, yeah. And then this one you can factorize, right? n power of 3 plus 1. Sorry, no, sorry. It's take out the n only. Okay. So take out the n. You have n power of 3 plus 1, right? Okay. And here the observation is that this is bounded by n plus 1 over n plus 1. Right? Definitely n plus 1 is smaller than n power 3 plus 1, right? The equality is because when can it be? No, actually, it's actually strict. It can be strict. Okay, it's definitely bounded by this because your n is at least 1, right? So yeah, so this is strict inequality. So then this cancels off, right? Okay, so it's bounded by 1 over small n, and therefore you can bound it with 1 over big N. Okay, therefore your n greater than 1 over epsilon already does the trick. Okay. Right, is that okay?
Yes, I get it, Doctor.
The trick here is first you look at this. The usual trick is to find some kind of bound that will kick away the constant. This is a constant. You find some bound that doesn't contain the constant. And after that, you may try some factorization to simplify the equation. And then these kind of things you can also then you find some kind of bound that kind of works on here you see that n plus 1, this is n power 3 plus 1. They are about the same already, except that this is a 3, this is a 1, right? So you can find a bound by reducing. So you obviously this will be bounded by n plus 1 in this case. So this is a general way to look at such type of how you set certain boundaries to your equation. Okay, this will give you some practice on using bounds. Yeah, because later when you study limiting processes, knowing how to use bounds, how to bound your function is very important, because frequently you want to find some limit of your function as certain parameters go to infinity. So but then directly evaluating that function is very difficult, right? So you basically you bound it first, then you show that its limit, right, is also bounded by the limit of the bound. Okay, that usually will lead to some simple results. Okay, so here you will get some exposure and ideas. Okay. Okay, so that will be question 7. And then maybe we can go back to question 4 now if if Ida Maisara is ready.
Hi, Doctor. Can you share me right now?
Yeah, you can share your screen now.
Okay. Okay, wait. Can you see it? Can you see the screen?
Yeah, we can.
Okay. So the question for problem 4 is algebra of set. So for the first, it is union x from 0 to 1 for x minus 1 until x plus 1. So first, for s equal to 0, it is from negative 1 to 1, and s equal to 1, it is from 0 to 2. So I sketch the sets, and for the union, it is from negative 1 until 2. Is it correct?
Actually, there are infinitely many sets. So what you are, so the 2 sets that you have sketched are the because your x is running from 0, right, until 1, right? So there are like infinitely many possibilities. So what you have shown are the 2 endpoints lah.
Okay.
So anything in between, they will be contained within -1, 2, right?
Yes.
So yeah, so that's why your union will be the largest set lah, -1 to 2.
Yep.
But just to make sure that this union here, there are infinitely many such intervals, yeah? It's just that because you take union, right, then you consider the largest of them lah, collectively. That's why you get -1 to 2, okay?
Okay. So for the second question is it is intersection for that set. So the intersection is the inside of the largest set. So it is from 0 to 1.
Yeah, that's right. So you take the so yeah, so the intersection, right? The part that is common to the part that is common to all, right?
Yeah.
Okay, so that obviously will be the interval 0, 1, yeah?
Yes. Okay. So for the third problem, it is for union k that is for natural number. So from 0 to 1 over k. So I try to substitute from 1 until for all the natural number, which until infinity. So it is from 0 to 1. Is it correct for the union?
Yeah, this is trivial.
This.
Yeah, because your set is, the interval is actually decreasing, right? So it's actually a decreasing interval for increasing k, right?
Yeah.
Yeah, your interval is from your longest interval is at the beginning. Then it starts to shrink, right?
Yes, start decreasing.
Yeah, the longest interval already is at 0, 1. Then for further k, it will start to shrink. So therefore, yes. Therefore when you take union, definitely it's just equal to the largest interval, which is 0, 1. Okay. Yeah, that's
okay. For the last one, so for the last one is intersection for the set is only 0. Is it correct?
Yes, it is. It's a singleton. Because all these intervals, they only share one common point, which is the endpoint, the left endpoint 0. The rest of them, or they will not share anything, right? As you take the limit.
Yes.
Okay. So in fact, this part 4 here shows an important representation of singletons numbers. In fact, numbers, right, can be represented as a set operation of infinitely many intervals. So this is actually a very useful way of representing singletons, yeah, using infinitely many intersections of these intervals. So okay, so maybe I give you a further example of part 4, but it's correct. All right. Okay, thank you, Aida. Okay, so I'm going to give you a generalization of part 4. So if you take intersection of this interval, open, left open, right close, yeah. So this way of writing is the same as writing it like this. It's the same, yeah. Okay, because basically this is just saying that your n is an element in the set of natural numbers. This one is basically just indexing it 1 to infinity. So it is, both of these ways are the same. Okay, sometimes in certain books they will write like this, sometimes certain books will write like that. Okay, but they just mean the same thing, right? So this one, if you sketch it out, right, this x is some real number. All right, so let's look at this. So you have basically x. So in the beginning, it'll be x minus 1, x, right? Then this is n, sorry, this is your n, 1. When your n is equal to 2, this will be x minus 1 over 2, x. When it's 3, it will be x minus 1/3 to x, and so on, right? So basically, if you sketch this thing here, it will be like this. This is your x. So x minus 1, right? Okay. Then it will get closer, right? Instead of being 1 unit away from x, now it is half a unit only, okay? Then this one is 1/3 unit, right? So it's like basically you have this interval, then this interval, then this interval, and then you take their intersection, yeah? Okay, you are finding their common point, yeah? So obviously the common point here will be the end point only. They only share a common point at the end point, okay? That's why this intersection is equal to the singleton x. Okay, this is a generalization of part 4, yeah, question 4, where in that case, the value of x is actually is slightly bit different, but about the idea is the same. Okay. And this result later we will use it in the course. Okay. And you note that this okay, so just leave it like that. That's this result, yeah. Okay, so we are done with tutorial 1. So anybody has any more questions about tutorial 1 before we move on to tutorial 2? Any more questions regarding tutorial 1? Okay, no more questions, right? Okay. So let's take a 5-minute break for a bit of stretching, right? Then we come back, yeah. Okay. We'll come back. So let's start tutorial 2. So for the first question, we have Hidayah. Is Hidayah here?
Yes, doctor.
Okay. Do you want? Yeah. Just go ahead and share your screen.
Can you see my screen?
Yes.
Okay, so the first question for tutorial 2 is to prove that each of the following sequences converge to 0. So for this question, I fail to find the suitable terms for the threshold n. So I prove by contact example. So by definition here, since it's said to converge to 0, so our A is 0. Therefore, by definition, it is bounded to this inequality. So to prove this inequality, I must show that this sequence is really less than the bounded epsilon for every value of epsilon greater than 0 when the n is greater or equal than the threshold n, and the threshold n is greater than 1 over epsilon. So I prove by contact example. Let's say I take epsilon equal to 0.01. So since I must follow this condition, so I substitute the value of epsilon, and then I get the threshold n must be greater than 100. So it's okay for me to choose, let's say n equal to 101 by definition. Then I substitute the values into the inequality. And then I get that it is true. This is really less than the bounded epsilon, which is here. And then therefore the equality is proved, hence the sequence xn equal to n over 2 power of n is converged to 0.
Okay. Yeah. So maybe I give some comments. Can you go further up? So you say, okay, you are saying that, but that condition like n greater than, okay, index n greater than or equals to big N, then suddenly there is a condition like larger than 1 over epsilon. I think that is something that you have to show. You cannot set it at that point.
Oh.
So it's also unclear what you mean by a counter example here, because here you want to prove that it converges to 0.
Yeah.
If you want to, but there's no counter example here, because the counter example is when you only have 2 possible outcomes. Okay, but here there are multiple outcomes, right? Okay, so you either converge to 0 or you converge to some other numbers. So if you are going to use a counter example, then your assumption will be it converges to some number that is not 0. You assume that it converges to some number that's not 0. Then you proceed to show that that's not true. And therefore, it converges to 0. But this is very tricky, because you are assuming that it converges to some number that is not 0. So how are you going to show that? So I think in this line of work, we do not, that this counter examples is not the right way to argue, to present the case. Okay, so okay, then maybe I give some comment by sharing my screen.
Okay.
And I'll come back, okay?
Or I present the second question and then you...
Yeah, okay, that's fine also. It's
Okay.
Part 2.
Okay, so this question also I prove by counter example. So I do like this. And then, but this one I take the epsilon equal to 0.02. And then the threshold n must be greater than 50. So I choose n equal to 51 because n must be greater or equal the threshold n. So I substitute the values, but it turns out that it is greater.
So I think the same problem.
Yeah.
You impose some kind of an arbitrary condition like n greater than 1 over epsilon. I think that is an arbitrary, that is something that we have to show, but you immediately just impose that condition. So yeah, okay, so therefore the argument has holds. Okay. Okay, so okay, let me continue from here. Okay, thank you.
Welcome.
It's okay. It's good that you try it, yeah. So that you have some idea how to construct the proof carefully. So let me share my screen. Okay, for the first one, so we want to prove that n over 2 power of n converges to 0, right? As n tends to infinity. Now, of course, if you use the machinery of calculus, the operational part, then definitely this one you can do it very easily, right? Because this will be just L'Hopital's rule. So because this will be the case of infinity over infinity, right? So you can use L'Hopital's rule. So this will be, you take the derivative, sorry, take the derivative, it will be 1. Take the derivative of, so anybody? What is the derivative of 2 power n with respect to n?
2 to the power of n ln 2.
Sorry?
2 to the power of n ln 2.
2 to the power, okay. So this kind of derivative, you have to express this as in the terms of exponential function, yeah? Okay, which if you know how to express it in exponential function, then it's very easy, right? So this exponential function, so this is your variable, so this is the constant, so it differentiates, so there will be log 2 times this thing, but this thing itself is 2 power n, okay? So yeah, don't forget your basic calculus, so you get this, right? So basically then this will be 0. Okay, it's very easy to see it from the machinery of from this machinery. But if you want to argue it rigorously, right, based on it is completely possible for someone at the, let's say, Form 6 level to do this question. Totally possible if the person has already learned these rules, right? They are not very difficult operations. But if you want to argue it at this level, right, then because it's totally possible for you to do this without actually having the idea of the boundedness using epsilon, okay? So this is what we want to do. So this is good for checking, right? If you're going to use the argument, the epsilon argument, so this is what you can do. So again, this will be a practice in playing with bounds, yeah. Okay, so you want to show that there exists some in threshold n such that this will be bounded by epsilon for all epsilon greater than 0 when your index n exceeds this threshold, okay? So basically your left-hand side is equal to just this. I can take away the absolute because this is definitely always positive. All right. Now, then the trick here is to try to find some kind of bound for this thing. And if you directly bound it like this, which you can do, but you will find that you have difficulty expressing n in terms of epsilon, right? So this is not very satisfactory. And therefore you have to find some bound here. But what is it? Okay. Now it turns out that in this case, if you know the binomial theorem, then your life will be much easier. Okay, binomial theorem. Right, a plus b raised to the power of n is equal to the sum of the binomial coefficients multiplied by a power multiplied by this a raised to the power of I, and this one is the complement. Okay, so your I is running from 0 to n, right? And we know that there's a basic inequality, basic result, which is if you sub in a equals to b equals to 1, your left-hand side will be 2 power of n, your right-hand side will be the sum of the binomial coefficients, okay? All right. All right, now it turns out that this is the part that helps you with the bound. So this thing, right, if you write it down in terms, right, this will be the first is 1 plus n1 plus n2 and plus a whole lot of things, yeah, until n, right? This is definitely bounded. Oh, sorry, this is definitely is this long, right? Okay, So does that give you an inspiration? What should this bound be? So if I show you this, that 2 power of n is equal to 1 plus this thing, what should this bound be? Anybody? So look at this form carefully, right? 2 to a power of n is equal to 1 plus all these things, right? So by using this relationship, I can set a proper bound for this thing. What is it? There are several possibilities, but there's one that actually convenient to work with. Let's give suggestions. Yeah, look at suggestions.
Is it 1 over 2 to the power of n?
Sorry, come again.
1 over 2 to the power of n?
1 over 2 power of n. Do you mean this?
Yeah.
No, it cannot be bounded by this because this is 1, right? Your n can be anything. So you take some n that's larger than 1, then it will already escape this bound. So it's not bounded by this. I want you to look at this equation here. This result here. This will give you some idea how to bound this.
N to n is less than n divided by 2.
Divided by 2. Bounded by n over 2. Okay. It makes sense? Yeah. So this is this is one example, n over 2. And then the next thing is what? So definitely in this case, it will be less than. This is strict, yeah. And then you can bound it with, no, but then let me see. Does it work? Does it work? Can you, oh, okay, so in this case, can you do something like this? You can't, so if you, okay, this bound is okay, yeah, it's correct, but it's not useful because the whole point is you want to express it in a form like this, right? Now, if you just replace like this, yeah, it doesn't work because this condition here will violate this part that you want. You are not getting this part. The index n is greater than or equals to big N, right? Because here if you set the inequality like this, it implies that your n is less than or equals to big N, yeah. So it doesn't work with, although you get a nice bound for n over 2 power n, it doesn't work in this case. All right. We're trying to work with this part here.
Doctor?
Yeah.
How about 2 over n minus 1?
2
2 over n minus 1.
bounded by 2 over n minus 1. Do you mean this?
Yes.
How do you get this? How do you claim that this is true?
Because whenever I put n, because 2 power of n, you wrote that will be until n choose n, right? N.
Okay.
And this is equal to, yeah. And it is bounded until 1.
Okay. Okay. So maybe you want to explain how you got to this bound.
Um, um,
Do you want to share your screen and maybe if you are able to write something on the screen, or
I'm not sure whether it is right. I just assume.
what's the idea? Maybe you can share the idea.
Yeah, sure. I will share the screen. Let me. Yeah, I cannot start to share my screen because there's
Oh, I have
someone.
to stop
Yeah.
sharing first. Yeah.
Okay. See. I make like this.
Okay, 2 power of n is definitely larger than n minus 1 over 2. Yes, you are right, because it's n, so that is, the right hand side is n choose 2, right?
Yeah.
Since there are many terms there, so definitely it's larger than one single term, right? Therefore, n over 2 power of n will be bounded by that. Okay, great. Yeah, you're correct.
Okay.
So then you have 2 over big N minus 1, right? So it will be bounded by, then you can use the 1 over big N minus 1. Like, you can continue, right?
Yeah.
Okay. So yeah, so that's nice. I think you get the idea, right? Okay. Let me just take back screen sharing.
Okay.
Okay. So let me clear the clutter a bit. So maybe I write down again, 2 power of n is equal to 1 plus n choose 1, n choose 2, so on. So Was it Umaira? SIT3001. No Umaira, is it? Okay. So n of these, so therefore it's bounded by n over n choose 2. Okay, because your 2 power n is larger than a single term, right? Because there are many terms here. So therefore 1 over 2 power n is less than 1 over n choose 2. Okay, and therefore I put an n here, right? So this is correct, on the right track. So n over n minus 1 over 2. So we'll cancel, the 2 will go up here, right? So so therefore this will be bounded by 2 over big N minus 1. This is definitely correct because because this is basically equivalent to 2n minus 1 bounded by this. Cancel the minus 1 cancel, right? Sorry, this will be the small n. Okay, so over here you will get your, so this is still true, right? This index n is larger than big N. It's bounded, so less than epsilon. Therefore, your n, as long as it's larger than 2 over epsilon plus 1, you are done. Okay. All right, that's very nice example of using the bound. Okay. So I hope this demonstration will give you some examples, right? How to think about constructing bounds. Yeah. So basically, and sometimes it's you might find that you cannot make progress because you are not aware of some basic results. So maybe it's just good time to refresh some of these results. Okay, but once you have those results, generally you should be able to make some progress. Okay. All right. Okay. Is that clear? Is that clear to the rest?
Yes, Doctor.
Yeah, of course, other possibilities. So, but I think over here, if you use any bound that is, if you use something like n choose 3, also it will work. Also. Okay, but it will not work if you choose a bound like n choose 1. The bound is too loose already, so you have to choose carefully. Yeah, choosing the order 2 bound, order 2 term, or any term that is a bit higher will work. All right, but of course you have to bear in mind that this order is increasing, then is decreasing back. Yeah. Okay, then we have the other one is we want to show that square root of 2n plus 1 over n plus 2 is converging to, the limit is converges to 0 as n tends to infinity. Again, this is not difficult if you use L'Hopital's rule, right? Because I'll just leave you to that. Yeah, this is clearly a case of L'Hopital's rule. Now, if you want to use the definition, right? So how would you approach this? So your left-hand side is equal to this. Okay, we can remove the epsilon because it's definitely positive, right? And how should you bound this? Any suggestions from the students? Please remember that this kind of problems have many possibilities. Yeah, there are many possible ways to show. So that the solution is definitely not restricted to just one. So anybody? No ideas? I got scared by the square root. I think the most important part is to work with this thing.
Can we do it like we times the cert n for the upper part and the bottom part, and we'll get something like we can get rid of the cert n above.
You're saying something like multiply with like this. Well, if you try something like this, maybe let's see. So this will be 2n, right? So plus minus, so this will be 2n minus 1. So denominator will be this. Okay. Maybe some progress here.
We can make the below part become n plus, means that cert 2n plus 1 over n plus 2 is less than cert 2n plus 1 over n.
Okay. Do you want to share the share screen? I let you. Maybe it's better if you.
But I'm writing on a paper.
You're writing on a paper.
Yeah.
So let me see if it is possible to if this is possible or not. So let me try. Just trying. So this is definitely bounded by 2n minus 1 square root of n plus 2. Okay, because this will be smaller, right? As you expand this, you will get square root of 2 times n minus square root of n plus 2 square root of 2 n minus 2. Is it getting clearer or more complicated?
What am I doing is that I'm not times with the thing with SIT2n minus 1. I just times with times the numerator and denominator with SIT_n only.
With square root of n.
Square root of n.
Okay. So let's try your idea. You're multiplying with square root of n like this. Is that correct?
Yeah. Then I'll get something like I'll get this thing will become
You would get something like this, right?
But what I do is the n plus 2, right? I make it like less than n first. Means that less than
okay.
square root 2n plus 1 over n plus 2. Bound it first. Bound it first, then only I make the multiplication.
Okay. So you bound this with well, okay. So this will be bounded by square root of 2n plus 1 over n, right? So this is okay.
Then I times the numerator
with this.
Yeah.
So that will be square root of 2n plus 1. Okay, then you probably have to do some expansion, right?
Yeah.
So that will be square root of 2 times n plus square root of n over n square root of n, right?
Then I split the fraction, become SIT2 over n, SIT2 over plus with 1 over
n.
Then I say this thing is actually less than SIT over n because this thing is less
by so you're saying this is bounded by square root of 2n.
Then
right.
I just eliminate the 1 over n because I know that 1 over n when the thing 1 over n is strictly larger than 0, right?
So
I just write like this only. I didn't have plus behind. I didn't have addition behind.
Sorry, this is bounded by what? Square root of 2 over n plus.
Because I know that 1 over n is wait. 1 over n is strictly less than 1, right?
Huh? 1 over n? Okay.
Less or
so you put one here.
I didn't put anything here. Okay, I put 1 here. Yeah, I put 1 here. Yes.
Okay, you can put 1. And then therefore this will be then you're on the right track already, lah. Right? Because this will be consistent with this condition, right? This can because your square root of 2 over n plus 1 less than this will cancel, so the square root of 2 will cancel, so you will have n square root of n larger than square root of n. So yeah. Okay. I think up to this point is okay already. So then you bound by epsilon. So square root of 2n. So sorry. So this from here you rearrange, you will get you rearrange this. Okay. So you will have your n will be larger than epsilon minus 1 squared as the denominator. There's a 2 here, right? Okay, you will get you will get this inequality. Is that so?
Yes, that's what I do.
Okay. Yeah, it's correct. Okay. So it's an interesting way to show your thinking. Yeah. So this is one. So the first thing is usually like I said, you get rid of those constant terms there first, right? And usually you can find this, and this is a good observation to simplify, because usually the numerator you simplify it is better. So then you get this, you have this thing already. Yeah, so there are many ways to do this. Over here, you can bound it with 1. You can also bound it with, I think this is also bounded by square root of 2 over n, right? Because square root of 2 is larger than 1, so this is okay. And denominator n, this is n is larger than square root of n, so this will be okay. If you use this bound, the inequality here will be simpler lah. So it will be this plus square root of 2 over n, so it will be twice of square root of 2 over n. Okay, and therefore this is bounded by the same thing. I change the small n to the threshold. All right, so this will be less than epsilon, and therefore this will be somewhat cleaner lah, but it's not necessary to have something that is clean. Okay, so n will be greater than 2 square root of 2 epsilon square. Okay, which is basically n larger than 8 over epsilon squared. Right? So there are many possibilities. All right, as long as you got until this part, there are many other possibilities to show. Yeah. Okay. So is it clear to everyone how you can solve this this problem?
Yes.
Okay. Okay for everyone. So then I think what time is it now? It's okay. So we still have maybe about 15 minutes. So let's go to the next question. Next question is by also finding limits, right? So Nabiha. Is Nabiha here?
Yeah.
Okay, can you share your screen?
Is it available now?
Okay.
Okay. So the second question is find limit of the following sequences. For number 1, this is the sequence. So we find the limit as n approaching infinity. So what I do here is I divided each element with n cubed. You can also apply L'Hopital's rule here, because as n approaching infinity, this will be infinity over infinity. But what I did here was I divided each element with n cubed.
Okay, that's actually a good strategy as well.
Okay.
And then you take the limit. Yeah, then it's clear that because those are 1 over n square and all that, so they all go to 0.
Yeah.
Okay.
So we are left with 1 over 5. It is 0.2.
Okay. This is if you use the machinery of taking the limit. All right. Then the next one.
So this is the second question. So we find limit as n approaching infinity. And what I did here is also the same as 1. I divide numerator and denominator with the biggest, with n, with the biggest degree as the numerator. Because for this numerator, the biggest degree is 1 because this is square root of n squared. So it's 1.
Okay.
Okay, so we divide this numerator with n and also the denominator. So 1 over is actually equals to 1 over SIT n squared. And then this is both square root here, so we can write it like this. And then we simplify this one. We will get 2 minus 1 over n squared.
Yeah.
So, and then as n approaching infinity, this will approach 0.
Okay.
And we're left with SIT2.
Okay, great. So it's a similar kind of strategy, right? To simplify the term so that you end up with something that is 1 over some function of n, right?
Yeah.
Because you know that will go to 0 when n becomes very large, right?
Yes.
Yeah. Okay, great. So yeah, so for this problem, you just need to use the machinery because it's just asking you to find the limit. Okay, so the first question is asking you to prove. So to prove, you will have to resort to the epsilon argument, right? But if it's just finding, you don't actually have to do that. Although if you want, you can actually, because to prove it, you first have to have some idea about the limit, right? You don't have the limit, then you because you still have to set that limit, right, in order to prove it, right? So yeah, so this question is basically just asking you to use the machinery to find. Okay.
Okay.
All right.
Thank
Okay.
you, Doctor.
Yeah. Okay. So problem number 3 is Jinjie, right? Can you share the screen? Give examples of some subsequences.
Okay, hi, can you hear me?
Yeah.
Okay. So because the -1 to the power of n itself is already diverged, because it will go to 1, -1, 1, -1, and so on.
Actually, it's not diverging. It's
No.
It's oscillating.
Yeah, oscillating.
It's diverging means it goes to very large or positive or infinity. So, but then oscillating is a form of non-convergence, right? Divergence is also non-convergence.
Okay. So my idea to make it converge is I will divide by n. I divide by n, so it will actually become something like 1 over infinity equal to 0 and -1 over infinity is equal to 0, which will make it converge to 0. Okay, so for the second one, to make it diverge, I just, oh yeah, so this is not the diverge already. So right. This one goes wrong already because oh no, it's not a diverge, but it still fulfill the needed of the question needs. Means it is oscillating convergence because because the -1 to the power of n itself is do not converge to a certain number, so you just add or minus the certain constant and it will still do not converge. That's my idea.
Okay. Yeah, I think you have some misunderstanding about the concept. It's asking for the subsequence. This question is trying to give you some exercise on the concept of subsequence. But I think you are not showing that, demonstrating that. Let me show you what's going on.
Okay, sure.
Okay, so you have this sequence. Okay, basically if you write it down, it's so your n is in this, so -1, 1, -1, 1, -1. Okay. Pick a subsequence of this that converge. So an example is you pick all the ones. So a subsequence will be 1, 1, 1, 1, which you construct by deleting. So you can construct this subsequence, which is a just constant 1. With your k, so with your k is 2, 4, 6. Okay.
Okay.
Yeah, because this is a subsequence. It's actually nested. This sequence, you basically you delete all these things. If you look at the notes, right, about the meaning of subsequence, is some kind of a sequence within the sequence that you can obtain by deleting certain terms. All right. So you delete all the terms. You delete all the odd terms. So basically, a very simple thing is you delete all odd terms. All odd terms. You will get this sequence. This sequence definitely converge because everything is just a constant. It already converged to itself 1. Okay. Some that do not, well, there are many. So the other example is you delete. Another example is delete all even terms. So then you will delete this even term. So your subsequence will be -1, -1, -1. So it already converges to -1. Okay, this one converges to 1. Those that do not, there are many examples. You can kind of like delete you delete certain, you delete it with certain pattern, like you delete 1, 2, right? Then you skip so maybe something like this. Okay, you keep the pair, you delete this, all right, and so on. When you delete this, basically you see when you delete these terms, right, you still get -1, 1, -1, 1. It basically is the same thing, right? So you're deleting 1, 2, 3, 5, 6, and so on. So in general, you can find an expression for this, right? I leave that to you. So you basically you can verbally explain this, it will be fine, right? You make a deletion like this, you will end up with the sequence -1, 1, -1, 1, and so on, right? This is the 3rd term, this is the 4th term, this is the 7th term, this is the 8th term. But still, this sequence is oscillating between -1 and 1. All right, is that clear to you, Xingjie?
Yeah, sure, clear. It's my fault. I misunderstood the question.
Yeah, I think you the idea is about the subsequence, yeah. Okay. Maybe I think you had a misunderstanding. It's okay, yeah. Okay, so we are actually running out of time already, so it's okay. We will stop until problem 3 for today. We can continue this next week, yeah. Problem 4, 5. Okay. And then we can already do 6 and 7 now. Okay, so like to assign question 6, 7. 7, there are 3 parts, so maybe 1 part for 1 student. So any volunteers? Problem 6, 7, there will be, I'll ask 3 students to do lah. Any volunteers? One Yuqing, 7-1, okay. Farah 7-2. Okay. 6 and 7-3. Nurul Izati 7-3. Okay. All right. How about 6? Not that hard actually, number 6. Okay, Zafira. Okay, great. The idea is to use bounds, yeah? Okay. So maybe I just quickly give you some idea. When we want to show integrability, right? That means you got some function here. I want to show that it's integrable, right? That means you're trying to show that this integral exists, okay, and evaluates to some number, okay? You don't actually have to evaluate it. You just, so basically if you have some function like this, for example, like this can be some function, right? So this is AB, right? So basically integrable means this area is, you know, you find this integral. Of course, it maybe, let me slightly do it like this. It can be any function. It can be some very weird function that's continuous. Maybe something like this. Okay, doesn't matter. So you will have this area, right? Okay. So definitely this integral, right, is bounded by its the integral of as follows. Okay, it's definitely bounded by the absolute because well, if you have absolute, right, then it's always positive, right? Just to give you some idea, like maybe if your function is like this. So if you integrate this function, so you're going to get some negative value, right? The integral is going to be some negative value, right? It's definitely bounded by the absolute because the absolute is always positive, okay? Now, in this kind of situation, sometimes you do not actually have to. So you know this relationship, right? And then there's also one more relationship which you can use. So the integral the integral of the absolute, right, is bounded by the absolute of the integral is bounded by the integral of the absolute. Okay, you can use this relationship. This is actually just a geometric relationship. You just make some sketches. Wait, just okay. Just make some sketches. Okay, so suppose you have some function like this. Okay, if you evaluate this, right, so this will be positive, this will be negative, right? Okay, if you evaluate this curve, then you take the absolute. Okay, it will be bounded by the following. So if you take the absolute of the function, this will flip like this, right? The negative part will flip up, right? Because this curve is the absolute of fx. Okay, the negative part flips up, right? So the integral of this thing, okay, to integrate this thing, it cannot go out of the integral of this absolute function, okay? So and over here you can actually make some additional bounds, right? For example, if you know that this is bounded by, so if this curve, right, is bounded by some constant, right, it will also work, okay? Like for example, this area under the curve is bounded by this rectangle, okay? If you can find this constant, right? So as long as you can find some kind of bound, then it's integrable, okay? It doesn't require you to evaluate this integral, right? So I'm giving you some ideas how to proceed, yeah, to show that it's integrable. All right, okay, so we will stop here for today. And please remember to sign your attendance in Spectrum, right? Okay, so thank you for listening. I will end the session now.
Thank you, Doctor.
Okay, thank you.